Welcome to G Fun Facts Online. Today, we are abandoning the classical laws of physics to explore a breakthrough that sounds like it was ripped directly from the pages of a science fiction novel. We are talking about the creation of solid light. Imagine for a moment a river that flows endlessly without any friction whatsoever. It glides perfectly. But if you were to look at that river under a powerful microscope, you would see that every single molecule of water is locked into a rigid crystalline grid, exactly like ice. If you push it, it flows like a liquid. If you analyze its structure, it is a rigid solid. This is what physicists call a supersolid. It is a state of matter that is essentially a paradox. It inhabits a kind of quantum purgatory, where it is rigid yet fluid, stationary yet flowing. For over 50 years, this concept was a theoretical ghost. It was a mathematical possibility that seemed to contradict our most basic intuitions about how the universe works. Solids are supposed to be rigid. They resist flow. Fluids are supposed to flow. They lack rigidity. To be both is to defy classical logic. And for decades, the hunt for this impossible state was confined to the absolute coldest corners of the universe, inside laboratories cooling atoms like helium-4 or dysprosium to temperatures within a whisper of absolute zero. But recently, in a landmark achievement, researchers have found a new medium for this impossible state. They didn't use atoms. They used light. A team of researchers from Italy's CNR Nanotech, along with collaborators from Princeton, has successfully coerced light into a supersolid state. They have created a material that exhibits the rigid crystalline structure of a solid while simultaneously flowing with the zero viscosity of a superfluid. And they did it using photons. This is not just a laboratory curiosity. It is a proof of concept for a new state of matter that opens the door to technologies we have only dreamed of, from processors that think with light to circuits that conduct energy without any loss. So how do you freeze something that travels at nearly 300 million meters per second? That is the question we are going to answer today. To understand how light can become a solid, we first have to appreciate why this is so difficult. Light, by its very nature, is the antithesis of a solid. It is energy in motion. Photons, the massless particles of light, do not naturally bind to one another. They are antisocial. If you shine two flashlights' beams across each other, they don't crash. They pass right through one another like ghosts. To freeze light into a solid structure, you have to perform an act of fundamental transformation. You have to turn light into matter. This requires a magic trick of condensed matter physics, known as the polariton. Because photons don't interact, we need a mediator to make them talk to each other. In these experiments, that mediator is something called an exciton. This happens inside a semiconductor material, specifically gallium arsenide. When an electron in this material gets excited to a higher energy level, it leaves behind a hole. This electron-hole pair is the exciton. Excitons are matter. They have mass, and they interact with each other via electrostatic forces. The researchers trap photons inside a high-quality reflective cavity containing this semiconductor. The photon is absorbed by the material to create an exciton, which then almost instantly decays back into a photon, which is then reabsorbed. This cycle happens trillions of times a second. It happens so fast that the photon and the exciton lose their individual identities. They merge into a new quasi-particle called a polariton. This polariton inherits the best of both worlds. From the photon, it gets speed and the ability to travel over long distances. From the exciton, it gets mass and the ability to interact. Polaritons can bounce off each other. They can push and pull. They are effectively liquid light. But having liquid light isn't enough to make a supersolid. You need that liquid to organize. This brings us to the concept of Bose-Einstein condensation. In the classical world, particles are distinct individuals. But in the quantum world, particles like polaritons act like waves. If you cool them down or increase their density, their wave packets expand. Eventually, these waves overlap so much that the individual particles lose their identity entirely. They synchronize. They all collapse into the same quantum state, moving in perfect lockstep. This giant matter wave is a Bose-Einstein condensate. It is a superfluid. It flows with zero viscosity because all the particles are effectively one single particle. If you push one part of the whole wave moves. Now, scientists have created superfluids of light before. But a superfluid is not a supersolid. To get the solid part, you need crystalline order. And this is where the experiment conducted at CNR Nanotech in Lecce, Italy, truly broke new ground. The biggest challenge with polaritons is that they die young. Because they are part photon, they constantly try to escape the semiconductor cavity as light. Typically, a polariton lives for only a few picoseconds, or trillionths of a second. That is usually not enough time for them to settle down and organize into a crystal. The researchers solved this with a brilliant workaround known as a bound state in the continuum, or BIC. In quantum mechanics, a continuum state is usually one where a particle is free to fly away. However, by carefully engineering the microscopic structure of the gallium arsenide waveguide, specifically by etching it with a precise, periodic grating, the researchers created a condition of destructive interference. Think of it like a prisoner trying to escape a cell. Every time they try to walk out the door, a clone of them walks in the opposite direction, canceling their motion. The polaritons in a Bach mode are technically free to leave, but the interference patterns of the grating trap them in a symmetry-protected state. They cannot radiate. This trick extended the lifetime of the polaritons significantly, allowing them to accumulate in massive numbers. With the polaritons trapped and long-lived, the researchers pumped energy into the system using a laser. As the density of polaritons increased, they condensed into a superfluid. But then, something extraordinary happened. Instead of staying as a uniform fluid, the fluid spontaneously broke into a pattern. The density of the light modulated. It formed stripes or droplets arranged in a periodic grid. This involved two distinct types of symmetry breaking. First, gauge symmetry was broken, meaning the polaritons synchronized their phase to create a superfluid. Second, translational symmetry was broken, meaning the polaritons spontaneously arranged themselves into a crystal lattice, creating a solid. The researchers observed satellite condensates, which are distinct peaks in the momentum distribution of the light, confirming that the light had crystallized. Yet simultaneously, the phase of the light remained coherent across the entire structure. The crystal was flowing. They had created a photonic supersolid. Now, you might be wondering, what does zero friction mean in a solid? In a normal solid, atoms are locked in place. If you try to push an atom, it bumps into its neighbors, creating vibrations, which we call phonons, and heat. That is friction. In a supersolid, the atoms, or in this case the density clusters of polaritons, are delocalized. They are not sitting in one specific spot. They are quantum smeared across the lattice sites. Because they share a single quantum wave function, the fluid can flow through the crystalline structure without colliding with it. The solid part is the density modulation, the repeating pattern in space. The super part is the fact that mass, or photonic energy, can transport across the system without dissipating energy. It is essentially a superconductor of light. This photonic approach is a massive game-changer compared to the atomic supersolids discovered back in 2017. Atomic versions using dysprosium or erbium require cooling to nanokelvin temperatures, essentially a billionth of a degree above absolute zero. That requires massive, complex dilution refrigerators. Photonic supersolids, while currently tested at cryogenic temperatures around 4 Kelvin, have a clear path to room temperature. The binding energy of excitons in materials like perovskites or organic semiconductors is high enough that they can survive at room temperature. The structural engineering of the bound state in the continuum works regardless of temperature. We are looking at the potential for a supersolid chip that runs at room temperature. Furthermore, in atomic gases, interactions are fixed by nature. But in photonic systems, you can engineer the landscape of the solid. By simply changing the pattern etched into the semiconductor, you can create honeycomb lattices, triangular lattices, or even topological lattices that don't exist in nature. You become the architect of this microworld. Also, unlike atomic supersolids, which are equilibrium systems that want to sit still, photonic supersolids are driven dissipative. You constantly pump energy in with a laser, and light constantly leaks out. This sounds like a disadvantage, but for information processing it is a feature. It allows you to encode information in the flow and read it out continuously. This leads us to the applications, which are arguably the most exciting part. The realization of photonic supersolids is the blueprint for a new generation of technology. The holy grail of computing is the topologically protected qubit. Conventional qubits, like those in Google's or IBM's quantum computers, are fragile. A slight vibration destroys their data. A supersolid lattice can host topological states, which are modes of light immune to defects. If you encode data in the winding number of the superfluid phase across the supersolid crystal, the data is protected by the topology of the system. You could literally chip a corner off the semiconductor, and the data would remain intact because it is stored globally in the knot of the wave function. Then there are optical neural networks. Artificial intelligence currently runs on silicon chips that consume massive amounts of electricity to shuttle electrons back and forth. Optical computing promises to do this with light, which generates no heat, but light is hard to interact with. A photonic supersolid provides the missing link, a non-linear optical medium. Because the polaritons interact strongly, you can use the supersolid to perform logic operations. You can build a neural network, where the neurons are droplets of the supersolid. They can process information at the speed of light, with the energy efficiency of a superfluid. We are also looking at lossless energy transport. Imagine an optical circuit on a chip that guides light without any scattering losses. In a normal fiber optic cable, imperfections in the glass scatter light. In a supersolid, the superfluid nature means the light flows around imperfections without seeing them. This could lead to interconnects inside computer chips that transmit data with zero resistance and zero heat, solving the thermal bottleneck of modern processors. Finally, this allows for the simulation of exotic physics. There are theories in physics, such as string theory, or theories of the early universe, that are impossible to test because the energy required is too high. A photonic supersolid is a tunable quantum simulator. By shaping the lattice, physicists can create artificial universes with their own laws of physics. They can simulate how black holes evaporate or how high-temperature superconductors work, all within a chip the size of a fingernail. The road ahead is clear. The freezing of light is just the beginning. The immediate next steps for the research community involve achieving room temperature operation by moving from gallium arsenide to perovskites, or transition metal dichalcogenides. They also aim to move from 1D or 2D planar waveguides to creating a fully 3D block of solid light. And perhaps most importantly, the goal is to create electrically driven supersolids. Currently, the systems are pumped by lasers, but the ultimate goal is to inject electrons directly, like an LED, to create the supersolid state, allowing for direct integration into electronic circuits. For centuries, we have divided the universe into matter, the stuff you can hold, and light, the stuff that lets you see. The discovery of photonic supersolids blurs this line until it vanishes. We have taught light to stand still and hold a shape. We have taught matter to flow like a ghost. In this new state of zero friction and infinite possibility, we find the future of technology. We are no longer just observing the light. We are sculpting it, freezing it, and building the foundations of a new quantum age. The age of solid light has arrived.